Thank you for taking the time to watch this video. What I'm going to do here is give a brief comparison of two big ideas in calculus, the idea of continuity versus differentiability, and I'll do so with the graph shown on your screen. So the idea of continuity in calculus terms, we can say that f of x, like the function you see, is continuous at any x value equal to some constant a if the following conditions are met. First, the function value f of a must be defined. Second, the limit as x approaches a for the function must exist. We must have a two-sided limit. And the third condition, to be continuous at any point along this graph, that limit value and the function value must be exactly the same. And visually, this just shows up as we can trace over this entire graph without ever lifting up our pen or pencil to draw a discontinuity, hole in the graph, asymptote, jump, anything like that. What we're going to compare that to is the idea of differentiability, which is a big idea in calculus working with what's known as the derivative. We say a function is differentiable at any x equals a along its graph if the following conditions are met. First condition, f of a must be defined. We still need to have a point, just like we did for continuity. And for the second criteria, we take the limit definition of the derivative, specifically at this value a. And we say the limit as h approaches 0, the distance between 2 points along the graph as that distance moves down to 0. For the quotient f of a plus h minus f of a all over h, that limit must exist, or the derivative must exist. And what this means is that a line tangent to our graph at a comma f of a has to have one clear defined slope. Can't have the possibility for more than one tangent line slope at this point, and can't have the possibility that we just can't make a tangent line. And so if you look on the graph is clearly continuous at x equals a. We can make a point, left and right hand limits match up. And it's also differentiable because there's only one good way that I can draw a tangent line running through that point. A tangent can only intersect the graph at that point, at least at the local level. And if I were to change the steepness of that line at all in either direction, I would run the risk of running through this graph at two different points. So that way of analyzing it is more qualitative. I'm going based on sight. You get more skill in quantitatively deciding if something's differentiable or not later on. So the question becomes after that, if we're thinking about slope along a graph, which really allows us to talk about if a function's increasing, decreasing, behaviors that we're used to from material in the past. How would a function not be differentiable at a certain point? How would we not be able to define the slope somewhere? So consider the graph that I'm drawing. With this point right at the top, looks like an upside down V shape because this example, I'm working basically off an absolute value function. And so let's set that vertex of this absolute value function at this x equals a that we've been referring to this entire time. And notice to the left of a, you have a slope for that linear portion that is positive, and it's also a constant slope. Off to the right, that slope clearly becomes negative, also a nice constant slope because it's linear. But now think of this in terms of limits, like that limit definition for the derivative, for defining a slope at a point. The slope as x approaches a from the left, we can see is positive. The slope as x approaches a from the right, like we saw and like we can see, is negative. Which must mean if we think in terms of limits, as a limit, the slope, and thus this idea of the derivative, does not exist at x equals a. for the same reason limits haven't existed before. The left-hand limit and right-hand limit do not match up. The left side slope and the right side slope do not look like they're going to be the same value at x equals a. So you have this case where this function is clearly continuous at x equals a. I can draw that without any jumps or discontinuities. But it's not differentiable at x equals a because I have no good way to define the slope at this point. And so this leads to a few key takeaways I want you to have from what I just discussed. First, functions are not differentiable at a few key spots. They're not differentiable at any place where a function would have a discontinuity. If you have a whole vertical asymptote, you don't even have a point, so how could you possibly define the slope of something tangent to that point? And also, like you saw from the absolute value graph, any sort of sharp corner, or another way of seeing those is also what's known as a cusp, but anywhere where you have an abrupt change in slope, and the slopes to the left and right around a certain point do not match up. And the last takeaway, if something's differentiable, if you can define the slope along an interval or along the entire graph, it implies that function is also continuous. But, as you saw from the absolute value graph, just because something's continuous does not mean it's differentiable. That does not mean you can define the slope everywhere along that graph. And so those are some big concept pieces as you make this transition from just talking about limits and continuity into this big calculus idea of the derivative, where we are defining slope for any function at specific points. Thank you for watching.